Welcome friends. Today we will be looking into the destabilization aspects of the dispersions. We have discussed about the emulsions and suspensions, which are the dispersed phase systems. As these both systems are consisting of unlike phases, that is, the suspensions consist of solids and liquids, and emulsions consist of liquids and other liquid which are in both of which are immiscible. So they are highly prone to become unstable because of various triggering factors. So in this specific discussion, we will be looking into those aspects which lead to the destabilization of the dispersed phase systems and mechanisms how they can be evaluated and can be overcome. So the learning objectives of this current lecture would be the understanding of the characteristics of stable dispersed systems in biphasic formulations, where the dispersed phase remains distributed without aggregation or separation during storage and use. Also, we will be looking into different instability phenomena such as flocculation, creaming, coalescence, cracking and phase inversion, including their causes, mechanisms and pharmaceutical consequences. Also, how these components like use of emulsifiers, suspending agents, flocculating agents and wetting agents influence the physical stability, redispersibility and patient safety would be another aspect of looking into these properties of the dispersed phase systems. This will also help us look into the analytical techniques used to evaluate the biphasic system, their stability including viscosity measurement, zeta potential analysis, particle size determination and stress based testing. This specific lecture will also help us in recognizing the critical role of chemical and microbiological factors in stability, including oxidation, hydrolysis and contamination, and also understand how to mitigate these with preservatives and proper storage. So, a stable dispersed system is a biphasic or a multiphasic formulation in which the dispersed phase, that is a solid, oil droplets or the gas bubbles, remain uniformly distributed throughout the continuous phase, which is usually water, for a prolonged duration of time. The dispersed particles should not aggregate, sediment, coalesce or separate during the normal storage and use. These are important in the pharmaceuticals because for the stable dispersed phase systems, that is suspensions, emulsions, foams and aerosols, it is important that the two phases are homogeneous, more or less homogeneous, and the separation leads to loss in the pharmaceutical property of the either suspension or emulsion. Also, it affects the properties such as dosage accuracy, that is uniform drug delivery, bioavailability, that is consistent absorption, patient safety and efficacy, as well as the shelf life and aesthetic appeal. Now, the criteria for stability of the dispersed phase system is evaluated on the basis of its physical, chemical, microbiological and kinetic stability. When we go for physical stability analysis, there should be no visible signs of phase separation, no caking or clumping in suspensions and no creaming or cracking in emulsions. Chemical stability, that is the API and excipients, should remain chemically intact and they should not interact with each other or degrade. Microbiological safety, it should be free from microbiological contamination throughout its intended shelf life. Kinetic stability, the system resists change over time but is not thermodynamically stable, delays natural process like flocculation or coalescence. What it means that during the course, though they are thermodynamically unstable, they should, during the course of their storage and usage, should not aggregate or form flocks or aggregates, which leads to the separation of phases and their pharmaceutical efficacy. So, the factors which influence the stability of dispersed systems are particle or droplet size, Smaller and uniform particles improve dispersion and reduce sedimentation rate. Zeta potential, higher surface charge, positive or negative, promotes electrostatic repulsion. Viscosity of the continuous phase, higher is the viscosity, lower is the settling of the particles and the phase separation. Emulsifiers or suspending agents, these form protective interfacial films or networks that hinder coalescence or flocculations. pH and ionic strength, these alter the electrostatic interactions and emulsifier solubility. Temperature, this affects the solubility, viscosity, phase behavior and chemical degradation rates, because with temperature the viscosity decreases and the settling rate of the particles increases, and hence the separation of phases occurs. So, the temperature has a direct impact on the viscosity. Also, it enhances the solubility of the ingredients, which can lead to solubilization and upon reduction precipitation. Also, chemical degradation can happen with temperature. So, the practical characteristics of a stable dispersed system are that how will you identify them is they should be easy to redisperse with mild shaking, and if any separation occurs, it maintains uniform drug concentration in every dose. There is no irreversible settling as in caking or cracking, remains visually appealing and pharmaceutically elegant. The industrial relevance of the design of the stable dispersed systems is due to its complexity of the phase behavior and interaction of multiple formulation components. So, it is important from the industrial perspective to not let the phases separate and put in place the use of the ingredients like the surfactants or increase the viscosity or balance the pH, so that there is no coagulation or aggregation of the like phases. So, there is a need to understand the rheology, colloidal science and interfacial phenomena. Advanced tools like zeta potential analysis, light scattering and accelerated stability testing are required to predict and enhance stability. More so because the industrially produced products have a shelf life and then they have to be transported and they reach the patients where it has to be in the most stable form. So, for the mass scale production and storage, understanding of these properties is very important to prepare pharmaceutically viable dispersed phase formulations. In the case of emulsions, which are thermodynamically unstable, the emulsions are unstable on thermodynamic grounds because coalescence reduces the system's interfacial area and energy, which is a favored process. The Garrett's definition of stable emulsion is that it maintains consistent particle size and count in the dispersed phase, ensuring constant interfacial energy over time. The practical versus thermodynamic stability is the stability as judged by the formulators or consumers is often subjective and not necessarily thermodynamic. For pharmaceutical emulsions, minor separations like creaming are acceptable if they can be restored with gentle shaking. Cosmetic emulsions, however, demand more stringent visual stability. The shelf life and kinetic stability is also important. So, the shelf life reflects the kinetic stability, where an emulsion retains its properties over a meaningful time frame without appreciable change. This is more about the rate of change than an absolute thermodynamic equilibrium. So, flocculation, this is the reversible aggregation of droplets within the dispersed phase, forming loose clusters while maintaining their interfacial film. The factors like surface charge on the droplets, insufficient emulsifier levels can lead to weaker protective barriers and coalescence. Electrolyte concentration, so modest amounts can be used to stabilize the dispersed phase, while excessive quantities may enhance flocculation. Example, sodium chloride helps stabilize some oil and water emulsions by reducing the oil separation. However, higher internal phase volumes tend to promote flocculation due to tighter packing of the droplets. Gum acacia can induce flocculation even at low concentrations. Despite taking all these precautions, the flocculation can still happen. Creaming refers to the upward or downward movement of dispersed phase under gravity depending upon the density between the phases. Creaming does not involve droplet aggregation, but rather the movement of droplets as individual entities. The factors which affect creaming are droplet size. So, larger droplets or aggregates cream faster according to the Stokes law. Higher viscosity of the continuous phase slows down the creaming process. Phase specific gravity, equalizing the densities between the phases, reduces the likeliness of creaming. Reconstitution, if no aggregation has occurred, gentle agitation can restore the emulsion to its original state. Application of Stokes equation can be used to qualitatively understand creaming and dependence on factors like droplet size, viscosity and density, and can help take care of the factors which are responsible for creaming, like if viscosity is poor, enhancing the viscosity can lead to lower rates of settling, and that can be determined using the Stokes equation. So, the law that is the Stokes law as is given in this equation, the various factors on which the creaming velocity is dependent is that it's higher is the diameter or the radius of the globules, higher is the rate of settling. The densities of the dispersed phase and continuous phase also have an impact. Viscosity, it is inversely proportional to the viscosity and directly proportional to the acceleration due to gravity. Now, upward creaming is generally observed in O by W emulsions where oil is less dense. Downward creaming is seen in W by O emulsions where water is heavier. The factors which affect creaming are the size of globules. Large globules cream faster. Density difference, greater the difference, faster the creaming. Viscosity, higher viscosity slows creaming, and storage conditions. Higher temperatures reduce viscosity and promote instability. Coalescence, this is the merging of droplets leading to the growth of larger droplets and eventual phase separation. A strong interfacial barrier which can be achieved using macromolecules or particulate solids can prevent coalescence. Use of auxiliary emulsifiers like natural gums or proteins to form thick protective films around the droplets can also be done. Coalescence, however, is irreversible and indicates instability. Surfactants play a major role in maintaining stability through mechanical strength. Interrelationship of symptoms of the destabilization like flocculation and coalescence. While flocculation is reversible, it can increase the risk of coalescence if the interfacial barriers are not sufficiently robust. Flocculation and viscosity. Flocculation contributes to higher viscosity, forming a networked structure within the emulsion. How agitation can disrupt this network and result in shear thinning behavior. Cracking is the breaking of an emulsion and is irreversible separation of the dispersed phase and the dispersion medium, that is the distinct layers can be seen. The coalescence leads to loss of emulsified state. The emulsion cannot be redispersed by shaking and it renders the product unstable. A clear separation of oil and aqueous phase can be seen and it is often accompanied by change of color, odor or viscosity. The causes of cracking could be addition of an emulsifier with opposite charge, cationic versus anionic, degradation or precipitation of the emulsifying agent, addition of a common solvent for both phases, growth of microorganisms which can affect the stability of excipients, thermal shock due to abrupt temperature changes. Phase inversion is the transformation of one type of emulsion to another, that is O by W into W by O, W by O into the O by W emulsion. This leads to change in the drug release, appearance, feel and therapeutic effectiveness. It is often irreversible and signifies instability. The causes could be the addition of electrolyte which changes the affinity of the emulsifier, changing the phase volume ratio. When the internal phase volume exceeds 74%, inversion can occur. At higher temperature, the solubility of emulsifiers may shift, changing the type. Also, use of emulsifiers which have different HLB values at different pH or temperature can lead to phase inversion. So these are the pictorial representation of flocculation, coalescence, upward and downward creaming, cracking and phase inversion. So the emulsion shelf life can be used to assess the stability, appearance, functionality, and this is used also as a criteria for acceptance. Packaging is critical due to potential incompatibility, material extraction or water volatile substance loss. The challenges could be the lack of rapid or sensitive methods to detect instability, reliance on subjective and prolonged observation should be done, which is generally under normal storage conditions as prescribed in the storage and labeling claim of the formulation. Stress based evaluations can be done to accelerate observation of potential instabilities, but require careful design to avoid eliminating the viable formulations. Key stress methods include aging and temperature cycling, centrifugation and agitation. Aging and temperature. Elevated storage temperatures simulate accelerated aging but may cause unrealistic reactions at higher temperatures, generally at more than 50 degrees centigrade. Temperature cycling between 4 degrees and 45 degrees centigrade mimics realistic yet stressful shelf conditions. The effects include changes in viscosity, freezing, damage to droplets and phase crystallization. Centrifugation simulates prolonged gravitational effects using the increased force. The moderate speeds of around 3750 rpm predicts shelf life effectively. Example, 5 hours of the rotation can predict a period of up to 1 year of storage. Ultracentrifugation of more than 25,000 rpm may rupture emulsifier films, creating abnormal separation layers. Agitation, this mimics the real world handling, exposing emulsions to mechanical stresses that can alter the stability. The Brownian movement, the microscopic random motion of the droplets plays a critical role in emulsions dynamics. Coalescence occurs predominantly when droplets collide due to this motion. Enhanced droplet impingement can also cause emulsions to destabilize or break under excessive shaking. For example, butter production illustrates how prolonged agitation leads to the coalescence of fat globules, separating them from the aqueous phase. Microemulsions may cloud upon brief agitation, while conventional emulsions can deteriorate with gentle rocking due to droplet interactions and thixotropic viscosity reduction. So, the agitation can also have various levels of impact depending upon the kind of emulsions being studied. Then auto-oxidation, polyethylene glycols or derivatives may oxidize, leading to undesirable odor, acidic byproducts and changes in the chemical composition. Non-ionic esters such as polysorbate 80 can degrade into stearic acid. This impacts the dielectric constant and exacerbates the physical instability, mirroring chemical changes, which is probably because of the hydrolytic instability of these esters. Then phase separation, which is the visual separation of the two phases when observed visually or measured volumetrically to distinguish between the reversible creaming and irreversible coalescence. The phase separation can be used as a parameter to detect the physical instability. The emulsifier impact, that is at low levels or high levels, what is the impact on the protection against coalescence. So, at low levels, that is at concentrations less than 0.1%, coalescence occurs rapidly. High concentrations between 2 to 5% prevent visible coalescence for years. Viscosity reduces the effect of mechanical stress or agitation, generally affecting the thixotropic systems common in the emulsions. Electrophoretic properties measures interfacial charges, revealing insights into droplet stability and aggregation tendencies. The particle size analysis for monitoring the droplet size and count helps predicting the separation and instability. Stability studies also focus on changes in viscosity during aging rather than absolute viscosity values. Instruments like cone plate viscometers are preferred for precise measurements. Coaxial cylinder viscometers can also be used, and they are very simple. Penetrometers are helpful for highly viscous emulsions. For the W/O, that is water in oil emulsions, initial rapid viscosity drop due to droplet flocculation, then destabilization over time occurs. In the O/W emulsions, initial increase in viscosity due to flocculation occurs, and then linear viscosity change occur over time. The ideal shelf life exhibits no slope in viscosity age plots, though acceptable systems may show changes which are very gradual. So, rather than the absolute changes in the viscosity, the rate at which it is changing are observed for evaluating the stability of the emulsions. Then the helipath attachment, which detects creaming or sedimentation before visible phase separation by measuring viscosity fluctuations at different sample levels, can also be used. Uniform viscosity patterns achieved with stabilizing agents like polysorbate 80 and methyl cellulose, these are observed, so they can be used. A decrease in viscosity often reflects particle coalescence, indicating instability and shorter shelf life. This can be measured by conducting tests in undisturbed containers to avoid artifacts from prior stress. Then replicate samples or specific recovery studies are essential to ensure reliable results. The viscosity is measured at multiple shear rates. The low shear rates reveal flocculation behavior, high shear rates indicate overcoming interparticle interaction, that is attraction, and potential impact of the reduction in viscosity. Electrophoretic properties, that is zeta potential reflects electrical charges on droplets and their impact on flocculation rates, less relevant for coalescence based instability. In the electrical conductivity for O/W emulsions, fine particles exhibit low resistance, which increases with aggregation. However, for W/O emulsions, coagulation manifests as the onset of conductivity. The methods for particle size analysis: microscopic measurements, which focus on particle diameter measurement along with the particle count measurement within a specific size category is done. Electronic counting devices like Coulter counter analyze particle volume, which gives the greater weight to larger droplets. This requires dilution, often with electrolytes, which can alter the sample's representativeness. So, that is the caution with these kinds of methods. Light scattering and reflectance techniques: the changes in light reflectance inversely proportional to the particle diameter is used for the determination of size. These can be used as a tool for predicting the shelf life. So, stable formulations show rapid initial increase in size followed by slower changes over time. Coalescence may occur without noticeable changes in particular size when emulsifier levels are low. Critical parameters to assess during shelf life testing are thus the electrical conductivity, light reflectance, viscosity changes, particle size variation, and chemical composition. Microbial contamination is also used to evaluate the stability. This can also be triggered with changes in the moisture and temperature of the environment. Aging and temperature changes can redistribute emulsifiers and preservatives, which can potentially have an impact on the microbial resistance. Next, coming to suspensions. A suspension is a biphasic dosage form consisting of finely divided solid drugs dispersed in a liquid vehicle. The physical, chemical, microbiological stability of suspensions is also important to maintain its efficacy, safety, and compliance. Unlike solutions, suspensions are also thermodynamically unstable and thus require formulation strategies to achieve the kinetic stability. Just like emulsions, the suspensions are also prone to get destabilized because of physical, chemical and microbiological factors. So, in the physical instability, sedimentation, that is the downward settling of the solid particles due to gravity, is observed. Caking, formation of a compact sediment that is difficult or impossible to redisperse because of the settling of the solid phase. Then flocculation, that is reversible aggregation of particles into loose clusters of flocks can happen. Oswald ripening, which is the growth of the smaller particles, and then position of these further position of the smaller particles to form larger ones can occur, and this changes the particle size distribution over a period of time. Chemical instability can occur due to degradation due to the presence of water, like antibiotics like erythromycin can get hydrolyzed. Oxidation can be seen with vitamins and corticosteroids. Photolysis, that is light induced degradation, can happen. This can be catalyzed by interaction with buffers, preservatives and metal ions. The aqueous suspensions support microbial growth. The microbial contamination can degrade the drug and vehicle or pose health risks. Preservatives like parabens, BKC are required to maintain the microbiological stability. The factors which influence suspension stability are the particle size and its distribution. Smaller and more uniform particles are required, and this leads to slower sedimentation as per Stokes' law, and enhanced stability and redispersibility. Micronization by jet milling, ball milling or any other technique can help achieve the target size. The vehicle viscosity must be balanced for physical stability and porability. Higher viscosity reduces sedimentation rate. So, the surface charge which influences the particle-particle repulsion. So, the zeta potential values between 20 and 30, absolute values which could be positive or negative, favor flocculation without hard cake formation. The wetting of drug particles which are present as dispersed phase. So, poorly wettable drugs tend to float or agglomerate. Wetting agents like sodium lauryl sulfate, polysorbates, sorbitan esters can be used. Ideal balance between the dispersed phase and the dispersion medium, that is a continuous phase, improves flow and dosing accuracy. The strategies which can help improve the suspension stability are flocculation control. Flocculated systems settle rapidly but are easily redispersed. Controlled flocculation prevents compact sedimentation and caking. Agents like electrolytes, that is NaCl or aluminum chloride, hydrophilic polymers like xanthan gum, surfactants, non-ionic types are preferred for less irritation, can help control flocculation. The suspending agents along with the increase of viscosity can help form a structured vehicle. The common suspending agents and their concentrations have been mentioned in the table 1 along with their types. The pH is also important, and the use of buffering agents can also help in maintaining the stability of drug molecules in the suspensions. Buffers like phosphate, acetate, citrate can be used. The preservatives are required for multi-dose products. The preservatives must be effective across various pH range. They must be compatible with excipients. Examples like methyl parabens, sodium benzoates are the kind of preservatives which can be used. The sedimentation volume can be used as an indicator of the stability of suspensions, which is the ratio of the ultimate sediment volume to initial suspension volume. Higher is the value, better is the stability. So, we can see in the figure 2 the original suspension, the suspension which has started settling along with the formation of a cloudy supernatant. So, in the clear supernatant we see the flocks are settling. However, in a cloudy supernatant there are still dispersed particles. This is generally observed with deflocculated suspensions. So, the F value when it is equal to 1, no sedimentation occurs. it is ideal physical stability, that is the dispersed phase is very uniformly dispersed throughout in the dispersion medium. The F equal to 0 means all particles have sedimented and compacted, indicating complete instability. So, higher is the F value, better is the redispersibility and physical stability of the suspension. Degree of flocculation, which is a ratio that compares the sedimentation volume of a flocculated suspension with that of a deflocculated suspension. So, it can be calculated using the formula beta is equal to F upon F alpha, which is the V flocculated upon V deflocculated. So, it can be calculated according to this formula. So, if beta is greater than 1, it indicates flocculation, higher volume of sediment. Beta equal to 1 indicates no flocculation or similar behavior to deflocculated system. Higher beta indicates better redispersibility due to looser sediment structure. So, it is a visual representation of flocculated and deflocculated suspensions. So, the flocculated suspensions over a period of time lead to the formation of cake. However, the deflocculated suspensions also form the cake, but their supernatant is still cloudy. However, the flocculated suspensions form a clear supernatant. The sediment also formed in the case of flocculated suspensions are porous. However, hard cakes are formed in the deflocculated suspensions because of the loose structure of the flocks, and they are more dispersible and easily dispersible in comparison to that of the deflocculated cakes. The redispersibility thus refers to the ease with which the sediment particles in a suspension can be redistributed throughout the medium upon agitation. This ensures uniform dose delivery, prevents dose dumping or subtherapeutic effects. It is important for patient compliance in multi-dose containers. This can be tested using a 100 ml graduated cylinder containing the suspension, keeping it undisturbed under visual examination. The cylinder is then mounted on a mechanical shaker that rotates 360 degrees at a constant speed, typically 20 rpm. The time in seconds or the number of rotations needed to redisperse the sediment is recorded. So, the cylinder is kept undisturbed under visual sedimentation observation till no more sediment is formed or till the values remain constant, that is the the final sediment volume is not changing. So, the less time and fewer rotations indicate better redispersibility, physically stable suspension. More time, more rotations means redispersibility, physically unstable suspension. So, to conclude, the stability of emulsions and suspensions is vital to ensure therapeutic performance, patient acceptability and regulatory compliance. Proper formulation and selection of excipients can prevent stabilities like coalescence, caking, thereby maintaining uniformity and effectiveness of the biphasic dosage forms. Subjection to stress testing such as temperature cycling and centrifugation provides predictive insights into long-term product behavior and helps refine the formulation to withstand real-time conditions. Viscosity and particle size trends offer practical indicators of physical stability, and their constant monitoring aids in predicting product shelf life and potential failure points. So, suspensions and emulsions require tailored strategies for stabilization, and understanding their distinct physical behaviors allow formulation scientists to enhance performance and patient outcomes. So, thank you very much for your patient hearing.